Thanks. I'm Michael Jarret. I'm presently at Perimeter. I'm also doing some work with Booz Allen, and I'll be working there shortly. This is joint work that I've done with Brad Lackey, who is not here today, but he will be. Kiana Wan, who was my student at Perimeter, and she's now a graduate student at Stanford, and Aiki Liu, who is also my student at Perimeter, and she is now at Caltech. Okay, so I'm going to start this talk in a really non-standard way with a poll of the audience, because I feel like maybe this will help people come from the same perspective I'm coming from. So who thinks that adaptive adiabatic optimization is something worth considering? That is, adapting your adiabatic protocol in response to measurement outcomes. Okay, decent amount of hands. Who thinks this is a reasonable proposition? That is, assuming the existence of an oracle that upon input a Hamiltonian returns the value of its spectral gap. That's about what I expected. Now, if you give this some thought, these are pretty much the same proposition to a large extent. Now, obviously I'm waving my hands there because it says modulo nuances. There are definite nuances. But since you basically want to control the speed at which you adjust your annealing schedule with respect to the size of the spectral gap, these are two things that are very closely related. Okay, so let's do a little review. The Adiabatic Theorem says that if you scale a Hamiltonian and you take, if you're doing an adiabatic protocol and you take your runtime big T to scale proportionally to about inverse gap squared, or somewhat more generally, inverse gap cubed, and there's a pretty general theorem that kind of sits in between those two, so we don't have to go all the way out to gap cubed. You get convergence to your ground state the whole way through, right? So the goal is to start with your initially prepared ground state, slowly evolve, and end with the solution to some problem of interest. And I'm assuming this is all common knowledge to people in this room. Okay, so this is kind of our starting point here. In 2001, Roland and Cerf showed how to do adiabatic Grover search. They do this with a completely connected Hamiltonian corresponding to a complete graph as your driver. And they do this using a very tailored schedule that reflects the fact that the spectral gap is changing. Okay? And instead of achieving 1 over gap squared scaling, achieves scaling 1 over minimal gap. All right? And the way they do this is they're going to evolve quickly until you get near the minimum gap, slow down, then speed up again. Okay, this is what it looks like. So you start with this initial driver here, and this is some cost function. And for Grover search, it is just zeros and ones everywhere, and the goal is to just find the zero. That's all you want to do. And this is what their schedule looks like. I think, if I recall correctly, big T is physical time, S is interpolation parameter, unless I screwed up my axes, which is totally possible. And this should be eigenvalues, not gap. So this here is the first excited state energy, this is the ground state energy, and you can see you spend most of your runtime just right around the minimum gap, and that's where you're going slowest because you want to guarantee convergence the entire way through. Okay, so this gives you O root V scaling, which is exactly what you would get out of Grover search in the circuit model or whatever else. And this also happens to be O1 over minimum gap for this particular problem. Okay, so now what happens as soon as the cost function is not this nicely behaved symmetric thing? Well, this is going to happen in many cases. For instance, suppose you're given SAT. Your cost function is going to return the energy of a particular bit string. It is not going to return 0 or 1, which is what you would want out of a SAT solver. Or you could have some implemented Hamiltonian with some known static noise in the system, right? And, you know, to get something from this form here down to this form here, into a form like that, you might need to do some really expensive pre-processing. And so we don't want to do that either. So the standard approach that we typically are going to go with is either guess an annealing schedule or just guess a runtime and go with it. But if you want to prove things based on this, there are some techniques that can sometimes do better. But again, you're going to get 1 over gap squared or 1 over gap cube scaling. And then the runtime of Grover is then, well, this is no good, right? We're right back at classical. if that's what we have to go with. If we're trying to do unstructured search, and we just introduce a little bit of noise or something like that. So what do we do? Well, there's some approximation, heuristics. Maybe these work. That's not good enough for me, and hopefully it's not good enough for other people in the room. We'd like to be able to prove some stuff and say some things with certainty. All right, so let's just take a look at some really idealized cases. Here, this Hamiltonian is the standard Grover search Hamiltonian as far as the driver is concerned. So it's that all-to-all connected guy. And the cost function here is all zeros and ones when it's these WGs reweighted by whatever number I put in front of it. And here is just some random thing. And so you can see that, well, you may start off following one of these reweighted Grover guys. So this is probably 0.5. But if you happen to end up with 0.35, it's way over here, and 0.2 right out here. And as it turns out, if you follow the random guy, none of these actually offer a good approximation. So following the schedule for any one of these, other than this, actually something designed for this, is not going to give you what you want. So you got to come up with some way to follow this thing. And so that's what we're going to do. So we want a strategy that, at least at the outset, is not a heuristic. We want it to be reliable and presumably can be performed. And I'm going to abuse that a bit during this talk. And then maybe we'll build some heuristics on top of that. We're not there yet. That's work in progress. OK, so the setup is I have a fixed driving Hamiltonian H naught. You're going to hand me a cost function. I don't know it. I'm allowed to query it. And my job is to produce the best possible annealing schedule and its result. And I want it to be optimized at the outset. So the two questions, or the many questions you should be asking, is even with this oracle that is capable of estimating the spectral gap on input the Hamiltonian, how many queries do we need? Because if we need too many queries, it doesn't even matter that we have this powerful device, right? This is no good. Then you want to know how optimal is the schedule we find, right? So maybe, based on a reasonable number of queries, we get some schedule that does not get us very far. And then the third most important question that everybody who raised their hands for one of my two questions raised their hands for, and not the second one, is assuming that these two things work, well, can you even implement such a thing? OK, so we'll need a few tools. First, we'll need some adaptation of the Adiabatic Theorem, a really simple adaptation of the Adiabatic Theorem. We'll need Vowels Inequalities, and some spectral graph theory. And when I say some, I mean a lot. It's a 40-something page paper, and 30 pages are just spectral graph theory. But this is for the implementation. So maybe we could get rid of this in the future and reduce it to more common physics-related stuff. All right. So here's the Adiabatic theorem. This is the one by Jansen, Ruska, and Sadler. This is probably the one that gets cited most, so I figured I'd go with this guy. And so here it is. It's kind of nasty. You see where the 1 over gap squared scaling is coming from. It's all these terms. But what if I impose this constraint? Well, then it becomes that. All right. And now things are really simple, and things are scaling like 1 over gap min. And this is actually something that you'll see coming up in a number of contexts. This is actually the constraint that sort of hand-wavy gives you the eigenpath traversal methods if you go through the Davis-Kahn theorem. This is something that you'll see in like these randomization methods. Anyway, so this is kind of the scaling you get. Now you see it is 1 over gap min scaling. So if we can come up with a method that guarantees that we're always there, we do get 1 over minimum gap scaling. OK, so let's start with Vowels Inequalities. The first thing is Vowels Inequalities say that for any eigenvalue of a Hermitian matrix perturbed by some delta, the difference between that and the corresponding eigenvalue of just the Hermitian matrix itself is less than the norm of delta. And this should be fairly intuitive to most people. And then we can convert that pretty readily just by using the triangle inequality to the gap of the Hamiltonian plus the perturbation delta minus the gap of the Hamiltonian itself is less than or equal to twice the norm of delta. And so then if h of s is some linear interpolation, which is what we're actually going to end up using in this case, you wind up bounding this difference in the gap for some delta s by this quantity here on the right. And you can just go and drop stuff in to, put the delta s h dot in place of the delta and exploit the fact that it's linear. Okay, so this is an algorithm I call the Bashful adiabatic algorithm, and I call it that because it's intended to be utilized in such a way that you take very, very small steps and never advance your Hamiltonian to the end, and you stop short every single time and restart. So you only ever go epsilon beyond what you've already computed. And it really just loops over that. That's what this delta s does, is it chooses a time step delta s that's small compared to the gap. And you notice that that keeps everything here small on the scale of the gap. So you're never changing the relative size of the gap through the protocol, right, in any given step. And then line 6 here, which is the next relevant one, gap stores the value of whatever this oracle get gap is. And we'll get to how get gap works in the case we explored later on. Okay? Cool. So this is how it works. You start out with your gap in the Grover problem. It's 1. And then you say, oh, Vowels inequality puts me somewhere in here. I'm above that black line and somewhere in the blue shaded region. You query, say, oh, I'm there. Do the same thing. Up, I'm there. All the way down. And you'll notice here, this is the lower bound, right? Because if you want to follow the adiabatic procedure, you got to always use the lower bound. And so you eventually get this nasty schedule, but we could have been smart and we could have used Vowels inequality in reverse and not just applied it looking forwards to smooth out the schedule, which would give us this. And you end up with something that looks very much like what you actually want for the gap the whole way through. Okay? But now probably the first and foremost question, how many calls do we need? Right? If we need order 1 over gap calls or 1 over polygap calls, this is no good. So here's some measure theory. So if we look at the size of the sublevel set, and here's a picture of it to make life easier. So the sublevel set is how much of the total time the gap function spends below a certain point. Okay, so we're measuring that. So if we're at 0.5, it would be like 0.3 to 0.7. So the measure of that would be 0.4. And as it turns out, if your sublevel sets satisfy this inequality here, that is the measure of your sublevel sets is always less than or equal to a constant times 2 to the negative k, where k is defined by the equation up here, then you need at most O log 1 over minimum gap calls. So you get logarithmic scaling in 1 over the gap, which is precisely what you want. Well, I mean, you'd like constant time scaling, but you're not going to get it. Okay. So, good, we only need log 1 over gap queries to the get gap, and this actually gives us a schedule that is accurate up to, well, it gives us runtime 1 over gap. It's not entirely accurate, but it's good enough. But, estimating the gap should be hard, right? Thank you, Fan Chung. She comes to the rescue. And so this is where we're going to explore a specific case. This should really be seen as proof of concept, and these techniques need to be advanced for the sake of actual further development. Okay, so I'm going to exploit Cheeger inequalities here, and we're not going to worry so much about what they are conceptually, because I don't have enough time to get into that, but an important thing is classically they measure kind of max flow min cut in a graph. And we can do a quantum version of that, and things get reweighted by the ground state. Conveniently, the denominator of this ground state is a measurable quantity, the denominator of the Cheeger constant is a measurable quantity in the ground state, as is the numerator, at least in principle. Might be hard to do, but in principle it can be done. Okay, so this makes it look like the Cheeger constant is a good thing to use, and all of the information is contained in the ground state, which our adiabatic process is already producing if it's working right. But the inequality, which I derive in another paper, is a bit too weak in the case of something like Grover search, which is what we're about to take another look at, except it's this Grover search with a ton of noise. And we have to fix that. So this on the right-hand side scales like root h. This scales like h. So that's quadratically weak. We need it to be tight. So in the paper, what we do is we tighten up the entire inequality so that everything scales like h. And kappa here can be thought of as something like a condition number for the problem Hamiltonian. It's not exactly what it is, but it's got that kind of a feel to it. Okay, so this is, I don't know why that's highlighted. Oh no, I do know why that's highlighted. This is the oracle for the complete graph. Don't worry about this guy finished schedule. I'm not even going to have time to talk about it. But basically what goes on is we find some value for h, the Cheeger constant. We find the root of some equation, which will be on the next slide, and we store that as the new value of h, and then we return some mess. And finished schedule just is like, oh, well, if we're at a point where we no longer understand things, all we're going to do is we're just going to use that envelope that we saw before from the sublevel sets, because we believe we are in that class. Okay, so it turns out that when you're on the complete graph and you're doing Grover type problem, this equation is a thing that's satisfied. And that's just magic for the time being. And that means that with this many queries to the cost function, we can find the root of this equation and get a decent bound on h itself. And you'll notice that it does not take us OV queries. It takes us about v to 2/3 to get us down to a point where we can demonstrate some sort of quantum advantage. And there's some balancing going on and some stuff that I'm pushing under the rug. This should say max. Yeah, this should say max, because you can never have less than root v. Okay, so I'm going to maybe talk some more about finished schedule. I have a few minutes. But let me summarize what we've done so far. We provide an oracular algorithm that achieves near optimal scaling and runs QAO with little knowledge of the cost function. But then, this is actually, a reasonable theoretical model for adaptive quantum adiabatic optimization, right? But then, more importantly, we counterintuitively demonstrate that there exists, at least in the complete graph case, and the case that corresponds to Grover search with some crazy problem that we don't really understand, this can be implemented efficiently, right? And that should be the really surprising part, is that, in fact, it's not quite as hard as it initially seems. So you can look at this, you could look at this either as a proof strategy or an actual algorithm. That is, you could take this and use it as a method for proving things. If you can come up with an oracle, then you know, oh, well, I know things that satisfy this oracle will run in time whatever, but maybe I don't actually have a good bound on the gap. Or you can use it as an actual algorithm if you can come up with that oracle, but it needs more work in order to get there. Now, the oracle itself can be improved, but we get what seems to be an asymptotically optimal result, so I wouldn't recommend doing that. You can generalize to multiple mark states or multiple zeros, and that should actually be pretty easy. Scare quotes on easy. More importantly, we want to generalize to other graphs. And I think the most interesting case to look at is the hypercube, right? Everything in between the complete graph and the hypercube kind of has hypercube-y or complete graph-y type things. And the hypercube is kind of the most disconnected case. So that would be the next place that we're going to look with this work. And as it turns out, this finished schedule thing that I brushed under the rug, what's going on there is a balancing of parameters based on how long it takes to estimate the gap and basically the size of the gap itself. So as long as you can estimate the gap in time scaling something like 1 over the gap itself, right, or 1 over some polynomial in the gap, you can still balance your parameters and do better than 1 over gap squared scaling. Let's see. Yeah, and so this is kind of another question that's been burning in the back of my mind is, what about classical algorithms that have access to the same exact oracle? Right, you got a classical algorithm, you can access this oracle for the gap, you perform the same exact procedure, there's nothing particularly quantum about it, so you've always got a state that's pretty close to the ground state of the Hamiltonian at any given point. Can you then efficiently simulate the process? Or not? So maybe this could be useful for some faster Monte Carlo simulations. And it's also, there's nothing particularly quantum about the strategy. So it's also possible that this can control divergence issues from like classical eigensolvers, which is something I've also been thinking quite a bit about. All we're doing is this iterative technique based on eigenvalue bounds. And so, yeah, this is just something maybe, who knows. But since I'm out of time, I'll end it there, and I won't talk about finished schedule, and leave it for questions.
So you talked about the case where, if I understood correctly, there is one gap, but as we know in spin glasses...
Multiple gaps?
Yeah, what if you have multiple gaps?
So as long as this sublevel set conjecture is obeyed, which is really, or I don't want to go so far as to call it a conjecture, but as long as this constraint about sublevel sets is obeyed, then you're going to get the same behavior. If you have multiple minimal gaps that are basically the same size, then you're going to get a multiplier by the number of gaps that you experience. But presumably there aren't so many of them that are all the same, you know, really tiny size, that this is that serious a problem.
So I missed at some point which graph exactly you're assuming is complete.
Sorry, when I say the complete graph, the driving Hamiltonian corresponds to a graph Laplacian. And so when I say the complete graph, I'm talking about the complete graph Laplacian as the driving Hamiltonian. So it's, I can even go back even farther. It's the same Roland and Cerf driver that they use, which is the all computational basis states. There you go, that guy.
Okay.